All right, let's dive right in. Today, we're talking about the secret world of drone intelligence. We're going to pull back the curtain on the incredible decision-making that transforms a simple flying gadget into this super sophisticated navigator of our world.
I mean, you've probably thought about this, right? You see a delivery drone zipping by, and it looks pretty straightforward. But getting from some warehouse all the way to your front door, oh, it is anything but a simple straight line. The real answer is this amazing mix of hardcore math, clever strategy, and believe it or not, some big ideas we borrowed straight from nature.
So the core idea behind all of this is something called path planning. The easiest way to think about it, it's the drone's brain. And it's not just about, fly to this address. It's about constantly calculating the absolute best way to get there, making new decisions every single second.
Okay, so let's break this down. We're going to start with the most fundamental problem of all, just getting from point A to point B. This is like the bedrock of all autonomous navigation. In the most basic scenarios, a drone's path is just pre-programmed. It's a lot like the GPS in your car. Operators basically set a bunch of digital breadcrumbs, or waypoints, creating this kind of invisible road in the sky. And yeah, that works great for simple open-area flights. But as you're about to see, the real world is, well, it's rarely that simple.
So, what happens when things get messy? How does a drone handle the totally unexpected? Because the second you leave that nice, controlled lab environment, things get really complicated really fast.
I mean, think about it. The drone has to deal with, well, everything. Skyscrapers, trees, maybe a flock of birds, another drone doing a power line inspection. All of a sudden, that nice pre-planned path is totally useless. The drone has to be able to think on its feet. It has to react.
And to solve this puzzle, engineers have come up with a couple of big families of algorithms. On one hand, you have the grid-based methods. These are the perfectionists. They meticulously check every single possible path to find the absolute mathematically perfect route, which is awesome, but it can be way too slow for a chaotic city street. So that's where the other family, the sampling-based methods, comes in. Their whole goal isn't perfection. It's finding a good enough path, and finding it fast.
And believe me, the toolbox for avoiding stuff is packed with seriously clever tricks. For instance, some algorithms create these invisible force fields around obstacles that literally push the drone away. Others are all about elegance. They calculate the smoothest, most energy-efficient curve to swoop around an object, which is crucial for saving battery while staying safe. It's just this constant, frantic, high-speed calculation happening all the time. Okay, but here's where it gets even more interesting. Path planning isn't just about dodging things. For a whole class of drones, the journey itself is the entire point of the mission. I mean, what if your drone's job is to map a disaster zone after an earthquake, or inspect every single blade of a massive wind turbine, or even pollinate an entire orchard of almond trees? Suddenly, just getting to the destination isn't the goal anymore. What really matters is what the drone does along the way. And this brings us to a really important idea. Multi-objective optimization. All of a sudden, there's no such thing as one single best path. The drone's brain is constantly juggling competing goals. It's asking itself, should I fly faster and save battery, or should I go slower, take a safer route, and make sure I collect better data? It's all about finding the perfect compromise. And this table here, it shows that trade-off perfectly. Look at Path A. It's quick, only 10 minutes, but you only get 75% of the data. Now look at Path B. Yeah, it takes longer, but you get almost all the data. And if you're on a search and rescue mission, that extra 20% of information, that could be literally life or death. It could be the whole reason you're out there. And just to be clear, this isn't some far-off sci-fi stuff. This is happening right now. Drones are out there helping first responders map disaster zones, helping farmers get more out of their crops, and making things like bridge and power line inspections way safer and more efficient. So, okay. We've got one really smart drone. But what if we could multiply that intelligence? Because the next giant leap in this tech isn't about making one drone smarter. It's about going from one to many. Seriously, what happens when you don't just have one drone, but 10 or 100 or even 1,000? This changes the entire game.
And this gets us to the incredible idea of swarm intelligence. Now, the most important thing to get here is that there's no leader. There's no single boss drone or central computer telling everyone what to do. Instead, every single drone just follows a handful of simple rules. And by interacting with each other, this amazingly intelligent, coordinated behavior just emerges. The whole group becomes smarter than any single part.
So where do you think we came up with these brilliant rules? We looked to the ultimate expert, nature. We literally study how ant colonies find the fastest route to food, how massive flocks of birds fly together without ever colliding, even how genes evolve over time. I mean, these natural systems have been cracking complex coordination problems for millions of years. We're just learning from them.
Okay, let's take ant colony optimization. It's so cool. Just like ants leave a chemical trail, when a drone finds a good path, it leaves behind a virtual pheromone trail. Basically, a digital signal saying, hey, this way is good. The more drones that follow that path, the stronger that signal gets. And pretty soon, the entire swarm has collectively figured out the most efficient route to the target, all without a boss.
Or what about particle swarm optimization? This one is modeled on a flock of birds. So imagine each drone is a bird. It remembers the best spot it has personally found, but it also knows about the best spot found by any other bird in the whole flock. It's this constant sharing of information. Hey, I found something good over here. No, wait, I found something even better, that lets the entire group zero in on a target incredibly quickly.
So where does this all go from here? We have this incredible technology. What does the actual future of autonomous flight look like?
Well, for one thing, it's already completely reshaping huge industries. Of course, logistics and package delivery are the big ones everyone talks about, but the impact this is having on farming, on disaster relief, on checking our infrastructure, it's absolutely profound. It's making these critical jobs faster, cheaper, and so much safer for everyone involved.
But just as we're getting really good at solving all the hard technical problems, a totally new kind of challenge is popping up, a much more human one. The lines of code we're writing are starting to have massive, real-world consequences for our society.
And this has sparked a whole new field of research called fairness-aware planning. The goal here is nothing less than to program our human values, our ethics, directly into the swarm's code. So, for example, how you make sure a fleet of delivery drones doesn't just end up serving the wealthiest neighborhoods because it's more profitable. How do you program it to provide fair, equitable service to everyone?
And that leaves us with the biggest question of all, doesn't it? We've gone on this incredible journey all the way from a simple line between 2 points to this complex, intelligent dance of machines working together. But the next step in this evolution? It's not about faster processors or better sensors. It's about our principles. And how we choose to answer this question of fairness will define the entire future of autonomous flight.